Hi everyone, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're going to walk through the brand new June 2026 New York State Chemistry Regents exam, cluster by cluster. This is the third video in the series where we're going to look at the blood Equilibria cluster. If you're looking for a different cluster, check out the playlist linked in the description below, where you'll find step-by-step walkthroughs of the rest of the exam. Let's get started. So the first thing we're going to do with every cluster is thoroughly read the question, full on knowing that we're probably going to have to come back to the passage and the figures. So equilibria in the blood. Red blood cells contain hemoglobin, which transports most of the oxygen from the lungs to the cells of the body. Hemoglobin is often represented by the notation Hb. Equation 1 represents oxygen in the capillaries of the lungs binding with Hb to form oxyhemoglobin. And then it gives you a equilibria. Figure 1 shows the process of gas exchange between the lungs and the body cells through the blood. Dissolved carbon dioxide is transported from the cells of body tissue to the lungs by red blood cells and in the fluid plasma of the blood. And then it gives you a figure. What I notice in this figure is as oxygen is leaving the blood cells, then CO2 is going into the blood cells and vice versa, right? So for question 11, it says, using collision theory, predict and explain the change to the rate of oxyhemoglobin production when the concentration of oxygen in the lungs is increased. All right, so we got to think in terms of collision theory, but we're also thinking about oxyhemoglobin and an equilibria. So what I'm going to do is reference this equation. I'm just going to write it down on the next page to make it a little easier. So essentially what we are evaluating in this equation is when we increase the amount of oxygen, what's going to happen to the amount of oxyhemoglobin production? Well, according to Le Chatelier's principle, if we increase the amount of oxygen, we're going to cause a stress on the system, thus temporarily increasing the rate of the forward reaction, which will increase the amount of oxyhemoglobin produced. But before you go and say that, be careful what the question is actually asking, because the question is asking you to use collision theory. It's not asking you to explain Le Chatelier's principle. Right, we know in terms of Le Chatelier's principle that oxyhemoglobin is going to increase, so we can definitely go ahead and write that down. But in terms of collision theory, we're thinking like there's more oxygen that can now collide with the hemoglobin. So the reason that that rate of production is increasing is because there's going to be more effective collisions with the oxygen and the hemoglobin. All right, for question number 12, it says, draw an electron dot diagram to model the gas that is released from the liver cells into the plasma. So we don't know what that gas is. Maybe you remembered it. I don't remember it, so I got to go back to the figure, which is what you should be doing on the test. So if we're looking at the gas that's released from the blood cells, hopefully we can notice right here, CO2 gas is being released. So in other words, this question is asking you to draw a Lewis dot diagram for CO2. All right, so in order to do that, you do need a periodic table because you have to know the amount of valence electrons. I'm going to teach it like I do to my students. Maybe this method resonates with you. Maybe it doesn't. But we have carbon and we have oxygen. And what we need to do is figure out how many valence electrons each of them has. So we'll go back to our table. Hopefully remember the valence electron trend. 1, 2, 3, 4, 5, 6, 7, and then 8. Yes, I just said 6, 7. All right, so here's 4 for carbon, and then here is 6 for oxygen. So what we have, each oxygen, and we have 2 of them, is going to have 6. So that's a total of 12 electrons to distribute. This has 4. So in our dot diagram, ultimately we have to distribute 16 valence electrons. Since carbon is written first, I'm going to draw it in the center. And I'm going to connect both of these by single bonds. Each bond has 2 electrons, so we can subtract 4. So that gives us 12 remaining valence electrons, or 6 pairs to then go ahead and assign around the molecule. So I'm going to put those pairs at the most electronegative atoms. So 1 pair, 2 pairs, 3 pairs, 4, 5, 6. And then I just tell my students to play around with the octet rule and make sure each element has 8 electrons, unless it's hydrogen, which these are not. So carbon has 1, 2, 3, 4, so that's a problem. So what I'm going to do is I'm going to take a pair from oxygen, and I'm going to share it with this carbon. And then I'm going to take another pair from the other oxygen, because we're still going to have less than 8, and share it here. So then if you do the check, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So carbon's good. I'm sorry, each oxygen is good. And then for carbon, 1, 2, 3, 4, 5, 6, 7, 8. So that will be our Lewis structure. I don't know how your teacher taught you to do this, but other acceptable responses, as per the state answer key, the state will accept this if you draw that. And the state will also accept it if you label the electrons differently. So if you recognize that each oxygen has 6 electrons, if you draw it like that with X's and dots or some variation of it, that's okay as well. All right, so a little bit more reading. Carbon dioxide formed in the cells of the body tissues reacts with water to form carbonic acid, H2CO3 aqueous. Carbonic acid then dissociates to form H plus and HCO3 to establish an equilibrium. In the human body, this process is catalyzed by an enzyme, carbonic anhydrase, which allows the body to maintain a healthy pH. Equation 2 represents the overall equilibrium. Students performed a laboratory investigation in a closed system to model the process in equation 2. During this laboratory activity, appropriate safety equipment was used and safety procedures were followed. Which statement predicts the change in the reaction rates of equation 2 if students added carbonic anhydrase during the investigation? All right, so we got to figure out what carbonic anhydrase does. So it talks a little bit about carbonic anhydrase here. And it says that the process, the equation 2, is catalyzed by carbonic anhydrase. This is just a recall question at this point because you just have to remember what a catalyst does. If you're blanking on that, a catalyst is just going to increase the rate of a reaction. It's not going to increase it one way or another. It's going to increase it in both directions. Right? So these answer choices are talking about how the rate of both HCO3- and the rate of CO2 is going to increase. Well, the rate of the forward reaction is going to increase, and the rate of the reverse reaction is going to increase. So we're going to pick answer choice 1 that says both productions are going to increase. Okay, then question 14 says apply Le Chatelier's principle to identify one change in the laboratory investigation other than changing the amount of water that would increase the concentration of H plus and describe how the change would affect the equilibrium system. So just like before, I rewrote the equation so we can look at it down here. So ultimately what we want to do is get the amount of H plus to increase and do something to ultimately cause the rate of the forward reaction to increase. All right, so there's a few different things we can do. We just can't change the amount of water. So first thing, notice we have a gas here. So if I am to tally up the total moles of gas on each side, I have 1 mole of gas on the reactant side, and both of these are aqueous, so I have 0 moles of gas on the product side. So recall that according to Le Chatelier's principle, if you increase the amount of pressure, the system is going to favor the side with the least moles of gas. So if we are to increase pressure, think which way we're going to shift. If you're thinking we're going to shift to the right because 0 moles of gas is less than 1 moles of gas, you're correct. So one of the changes you could do is an increase to pressure. If you chose that change, you would just have to justify that exact explanation. You could also increase the amount of CO2. Right? If you increase the amount of CO2, then the system is going to shift to the right to use up some of that CO2. So that was the second accepted answer. Then the third accepted answer would be that we could decrease the amount of HCO3 minus, because if we decrease that product, then the reaction is going to shift forward to create more of it. Right, so your description of the change just has to represent one of those with Le Chatelier's principle. So that's it for this cluster. If you found the video helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can look in the description, click the link, and move on to the next cluster.